Hello, Chemistry 12. This is Mr. Chan here. And today what I wanted to do was I wanted to touch upon the example that I gave you last day when we were talking about standard reduction potential tables and how we can use them to predict our products. Now, in this example, remember we had the zinc nitrate solution, copper nitrate solution, and we mixed them together. And we went through the example that was down here. Now, one thing I wanted to highlight for you at this point in time is notice the phase symbols of the products. Here I have zinc plus 2 ion, which is aqueous, and copper solid. So if we wanted to take this and see how we would look at this visually, what we would notice is as this reaction proceeds, we would notice a couple of things. First of all, we would notice the zinc would start to dissolve. To form zinc plus 2 ions. Okay, so what we would have is we would start getting zinc plus 2 ions. That is why when we take a look here, this is why we have the AQ. Now, what happens on the copper side is that the copper will then start forming a solid of solid here, okay? And so what will happen is you're starting to get little pieces of copper solid that's being formed in the bottom of the solution. Again, why is that? Because looking at the products, notice that we're forming copper solid. Okay. Now, when you take a look in your Hebden textbook, if you take a look on page 195, as you go through it, you will notice that on section 5.3, they actually go through, the tendency to reduce is on the upper left and tendency to oxidize is lower right. So tendency to reduce, notice, is on the upper left, while your tendency to oxidize goes down in the bottom right. Again, this is like your acid-base table. Now, as you flip through page 195, and then you go to page 196, and if you scroll all the way down to page 197, okay, what they do is they go through the exact same example. All right. Now, the one thing they do here on the bottom of page 197 is they talk about what if there's both reactants found only on the right. Notice like here, and notice it says that there's no reaction. Why? Because both undergo oxidation. What if both are ions like zinc 2 plus and copper 2 plus on your standard reduction potential table? They're both found on the left, so they can both only reduce, so there is no reaction. Now, then on the bottom of page 195, they talk about the reactant to be reduced is higher up on the table than the reactant to be oxidized, which is right-hand side. What you get is a spontaneous reaction. If you take a look on page 198, it says here, the reactant to be reduced, left side is lower on the table than the reactant to be oxidized, the right side. Notice here, copper and zinc plus 2. Notice their location. What you have is you have no reaction. So again, a reaction will all depend upon where the chemicals are. Are they undergoing oxidation? Are they undergoing reduction? And which is higher up? Is oxidation higher up or is reduction higher up? And depending, sometimes you'll get no reaction, like in this case number 2, or sometimes you might get a spontaneous reaction. Again, reduction is higher than oxidation. Now, as you scroll down on page 198, what they will do is they will give you a few more examples for you to walk through and for you to take a look whether or not it will react or not react. Again, for A here, notice the location, fluorine and bromine. This will occur spontaneously. Why? Because reduction is higher than oxidation. Notice in case B, you have the tin and manganese. It will not occur because both can only oxidize. And if the last example that they give you, in this particular case, you have lead and nickel. Even though lead will oxidize and nickel will reduce, the reaction will not occur because the reactant to be reduced is below the reactant to be oxidized. Okay. Now, my hope is you did have a chance to go through some of the examples and some of the exercises, number 7, 8, 9, 10, and 11, and 12. And hopefully you were able to sort of play around with the standard reduction potential table. Now, for today, what I want to do is I want to focus on question number 14. Now, question number 14 is you are still using the standard reduction potential table and all the concepts that we had talked about, but in a different scenario. So, for example, question number 14, it says you have been given 3 half reactions. A plus 2 electrons gives you A. B2 plus 2 electrons gives you B. C plus 2 electrons gives you C. The reactions are not in any order of tendency to reduce, but the following experimental data is found. Now, when you read through this, it says here, so A reacts with C, but it says A does not react with B. So how do we use the concepts that we learned last day to sort of solve this type of question? So, first of all, let's look at the first scenario where it says A2 plus reacts with C. So in this particular case, if we say A plus 2 reacts with C, what that means is A plus 2, which is undergoing reduction, is higher than C. Okay, which is undergoing oxidation. Now, how did I know that? Because going back to your notes, okay, it says up here, if we went back to one of the examples on page 198, so reduction is higher than oxidation, so therefore it is spontaneous. So if we go down to this particular case, I'm not going too quickly right now, that's how I knew that A2 plus reacts with C. And so reduction is higher than oxidation. So if I were to put this down here, because I'm just lacking a little bit of space, what I would do is I would put A plus 2, which is undergoing reduction, would be higher than C. Now, the second one, it says A plus 2 does not react with B. So if we were to take a look at this, let's see, let me just erase this here. Okay. Let me just erase that here. There we go. If I were to do this, and I'm going to say here, A plus 2 will not react with B. Now, what does that mean? So therefore, what happens is the A plus 2, which is undergoing reduction, is lower than B, which is undergoing oxidation. Again, how did I know that? Is if you take a look here in the example on page 198, here oxidation is higher up than reduction, so therefore no reaction. So what I've highlighted here in orange is basically exactly the same as what I had done here where I wrote in black. So here, if I were to take this information, I would put B up here because B is higher than A2 plus. So I'm just going to spread it out a little bit more. So how would we solve this? So now we know that we have this particular scenario. So I can write it out now. So I would go B plus 2 plus 2 electrons would be giving you B. A plus 2 plus 2 electrons would give you A. And then C plus 2 plus 2 electrons would give you C. So based upon this information that I've highlighted, that I wrote in red and wrote in black, I basically rearranged this equation A, B, C, changed it to B, A, C. Now, if you take a look at the answer on the back, if you take a look at question number 14, they basically said the exact same thing. So in this case, it says, in order for A plus 2 to reduce and allow C to oxidize, the half reaction involving A plus 2 must be above the half reaction involving C. And if they take a look at the B, it says A plus 2 does not react with B, then the half reaction involving A must be below the half reaction involving B. So basically, in the answer they gave you, it's exactly the same as what I had talked about up here in sort of determining the half reactions. All right, that is basically it. And hopefully you were able to understand this. You were able to comprehend what I was talking about. All right. If you have any questions, please feel free to see me and ask me questions. All right. Thank you very much. Have a good day. Bye-bye.